Hello friends, today let's solve count of smaller numbers after self again. Let's remind what is this question about. Well, given an array, we want to return an array that each value means the count of smaller numbers after self. So how can we get this result array? Well, for this 5, we'll count how many smaller numbers in 261 is 2, right? Because 2 and 1 are smaller than 5, so we write 2 here. For this 2, we can count the smaller number after 2 in 61. There only 1, right? So we write 1. For 6, there is only one number smaller than itself, that is 1. For 1, there is no number smaller than itself, so it's 0. So how can we get this result? And how can we use binary index tree here? Well, I think this question seems a bit unintuitive. Why? Because usually we iterate an array, we iterate from left to right. But this question asks about a smaller number after self. So how can we do that? Isn't it more intuitive if we iterate from right to left? Why? Let's see. If we first iterate from right to left, then the first item we meet is 1, right? We know this is the first item, so there is no number smaller than itself, we have seen. And then we meet 6. And as we already iterate from 1, so we know 1 is smaller than 6, so we write 1 here. And we continue, we meet 2. We know among the 2 items we meet so far, only 1 is smaller than 2, so we write 1 here. And we continue, we meet 5. We count in all the items we meet so far. And we know 2 and 1 are smaller than 5, so we write 2. Yes, so that means we can actually iterate from right to left. And when we meet one item, we just let maybe that bucket increment by 1, right? The count of that bucket increment by 1, or we call it a count. Okay, let's see the process again. Okay, the first number is 1, right? So we write the count of bucket 1 to 1. And what is the prefix sum means? Well, as the current value is 1, so we want to know how many item is smaller than it. Well, so we just want to know 0. Actually, there is no 0, so it's 0. Okay, then we meet 6. And the bucket of 6, the count should increment by 1, so that is 1. And we count how many buckets. Well, before 6, they have their count. Well, only this 1 has a count of 1, so the sum actually is 1. That means there is only one item that is smaller than 6, right? So that's the 1. And then we meet 2. So we increment the count of 2 by 1. So here is 1. And we count how many buckets smaller than 2. Actually, only 1, right? The count is 1, so we write 1 here. And we meet 5. We write 5 here. The count 1 here. And we count how many buckets from 1 to 4, only 2, right? This 1 plus 1, so we write 2 here. Okay, so it seems pretty simple, right? We just iterate from right to left, and when we meet every item, we increment that bucket count by 1, and the number in the result actually how many buckets are smaller than itself. We just accumulate that count. Yeah, that's simple. So in summary, we only need 2 functions here. The first function is that we want to quickly get the prefix sum, right? let's see if we meet 5. Actually, we want to quickly know how many buckets it's smaller than 5, right? We count 2. So how can we quickly get that? That's the function we need. The other function is that we want to increment this count by 1, right? We meet 5, so we write this count from 0 to 1. We need these two functions. If you think more carefully, these two functions are actually very familiar to us. We already solved a range sum query before. We use binary index tree. Recall that the query from I to j is get the sum between I to j, right? We actually use query 0 to j minus query 0 to I minus 1, right, to get this sum. And the update, we add the k, usually it's a delta, and to the numbers I. So here we update the count by 1, right, which means k is 1. So that means we can use binary index tree to reach our two goals here. But you will find another issue, that is the bucket. How can we quickly get the index of each bucket? Certainly, it's not efficient that we directly use the number as the index, because sometimes we may have a very large number, and sometimes we can even have a negative number. So it's not possible to directly use the number as index. Do we have other way? Yes. We actually call it mapping. Why? Because we want to know the -3, -2, what's the index of them. So we need this kind of map function. What we do here is that we actually want to get a hash set of this given array, because as we record, this count can be greater than 1. So that means there can be some duplicate numbers here. So we get a hash set, and then we sort this array. Why do we need to sort it? Because if we sort it, then if we want to know -4 index, it's very quickly. We can use binary search. So if we want to find the -2, then we just need a binary search a -2, and we get some index. Well, if you're not familiar with this arrays binary search, I recall we actually use this in longest increasing subsequence question. Well, that is given an array and the key, we return the index. If we know in this array, then we just return negative insert point and -1. But don't worry, because we build this A by inserting all the numbers. So that means definitely we will have this index. Okay. So that's the way we get each number's index. Okay, now let's write the code. Okay, this solution is under the condition that you are familiar with binary index tree. If you are not familiar with binary index tree, I highly recommend you to watch this range sum query video again, because in this video I explain what is the binary index tree. Okay, now let's write the code. First thing first, we need to map these numbers to another array. We call it A, but now we don't know the size, so we can actually write here void map. We pass these numbers. As I said, we need a hash set, so we call it a number set, new hash set. And for each number in numbers, number set add a number. Then we know its size, right? That should be A, the size of A. So numbers, actually it's number, not numbers. Number set dot size. Then we also need the index from 0. And for each number in number set, we actually A index plus plus equal to number. And don't forget, we need to sort this array. Okay, now we get this array. And recall, we also need a count array. So here we know the size, right? The count is actually each item in the array A. So its size should just be A.length. Okay. Then for we iterate from right to left, so I will equal to numbers.length -1 and I greater or equal than 0, I minus minus. So what we do here is we get the ID of this number, right? Number that will be arrays binary search A, search in the A, and the item will be numbers I. Is that enough? No, we should also +1. Why? Because, well, let's remind you what is a binary index tree. Oh, I'm not quite sure. Okay. Here, usually the binary index tree from the index 1, not 0. So that's the reason we want to +1, because it usually 1, 2, 3, 4, so on and so forth. Okay. If you don't familiar with it, please watch the video again. And yeah, so we +1. That's the ID. And then also we need the result. List integer. We call it result new array list. And the result add something. But don't forget, when we add something in the result list, we actually append. We added things in the end. But what we do is 0, 1, 1, 2. But what we should return is actually 2, 1, 1, 0. So we need the reverse result. So connections reverse this result. Don't just return this because it return nothing. So we return result here. Okay, so we add. What we add here is query, right? We query how many number of buckets before ID. So ID -1. And then we update the count array to let the count ID increment by 1. So update. Okay, we just simply multiply these two functions in binary index tree. So that is query into I. Okay, it's a result. It actually accumulation of all the buckets before this query. This ID, right? So if we want to query something, then the condition is I greater than 0, because we actually every time we minus it something, the result plus count I and I minus something. If you remember it correctly, that is a low bit I, and we return result. So what is a low bit? Low bit is simple. Low bit int I, we return I and negative I. Okay, this is query. And another function is called void. Void that will be update and I. So well, update, we need to update all the bit will cover this item. So that will, it will increment this I. So the condition will be I less than count.length, the largest possibly. Or I will be count I increment by 1 and I increment by low bit I. Okay, this update. This is the query. Okay, I think we finish it. Okay, thank you for watching. See you next time.